is the lowest attendance by half. It's the end of the semester thing. So this will be on the final. So there won't be a final in this class. So yeah. So let me quickly say a few words about the posters. So I think maybe most of you in this room have actually already sent me a poster. So if you send me a poster to have reviewed by email if it was before 4 p.m., I probably already replied with some comments. If it was after 4 p.m., I probably haven't gotten to it yet. So I'll probably do it tonight. So then, if you're planning to have the department printed, you need to send it to Chris Coleman, and the details are in the document. You have to do that by tomorrow, and then they'll print it, and it'll be available by the poster session on Wednesday. If you're not having the department printed, then this early review deadline of today, we need to talk to me or send me the poster. I can then I can relax that a little bit, because you're going to be on your own for printing and stuff. So then, a good time is my office hours tomorrow. So then after I send you feedback, if I say, after you make these changes, you go and send it, then you don't need to send me another version, and that'll be fine. So then the poster session will be a week from today. It's going to be in this room. We'll have some easels, so you can put them up on easels. I'll have some magnets, so some people can put them on the whiteboard here. And we may have a few other ways. I know some people are planning to do alternative presentations. So just as a reminder, you'll have the opportunity for some bonus points on your project grade, where the class will get to vote on whose poster they like the best, and the top 2 winning posters, the students there will get bonus points towards their grade. So I encourage you to vote in any way you like. This means that as someone who's trying to get these bonus points, I encourage you to try and get votes in any way you want, except for paying people. So no paying people for votes. But other than that, do extra stuff. Have a cool poster, have a cool demo to go along with it. So do what you can to get those votes. All right. So any questions about the posters, or how that's going to work? So be in this room again. We'll start a little bit early. So if you can get here a little bit early to do that, that'll be great for me. So I may have to go around and see all of them. And if you can plan to stay a little bit late, if you finish everything and I've seen your poster, then you can leave a little bit early. But if I happen not to get to yours until, say, 6:45, hopefully that's okay. If you need to leave early for something, please let me know ahead of time, so I'll make sure that I'll see yours before a certain deadline. But there should be plenty of other posters to see, so hopefully you'll have no problem wanting to stay past 6:45 if there'll still be plenty of other stuff to do. All right, so great. So I'll try and, I haven't finished grading all the projects yet. I'll try and get that done hopefully sometime next week. All right. So so we're going to continue talking about graphs, and so this will be in the context now of like these large social graphs. So think of like Facebook, or to think of the web with all the web pages connected by links. And we'll be focusing on communities. So finding communities in this graph. And this has kind of been a grand challenge of the data mining community and is not really all solved. There are some more mature techniques. Most of these have been developed, a lot of newer ones in probably the last 10 years, but it's not really a solved problem. And I think part of this is because there's not always these well-defined communities that people thought or hoped would be available in social graphs. I'm sorry, so if you think about these large social graphs, then you're going to have these, you can formally define a graph as a set of these vertices and the edges between the vertices, and these vertices in a social graph may be people, or if it's the web graph, these are web pages. Okay, so often this is fairly well defined. Maybe they're not actually people, but they're entities posing as some sort of account, right? So for a while, I forget whether, so there's this big controversy on Google Plus, I think, about every account need to be associated with a name, and the name had to be formatted as a first name and a last name, and there need to be an identity with it. And some people did not want to use this service without giving away something about their identity. But you can often think of these as people, but they could be. There are also some companies that have accounts on these social networks, and these also count as these nodes, and you'll often think of them in the same. The edges part is a little bit trickier to understand. So with web pages, these are often thought of as links between the web pages, and so then these are directed edges. So these are. We'll be mainly talking about thinking about graphs as being undirected in this lecture. So we won't worry too much about the direction of the link. So you can think of it. If you have a link, it goes both ways, or whichever way you want. In terms of the social graph, where these vertices are people, what constitutes an edge is a little bit less clear. And so this involves some sort of model. So if you're on Facebook and you're friends with someone else, that is a good way of constituting edge. But if you only comment on someone else's page, or maybe this is how you would measure whether there's an edge. Maybe if you've done some sort of commenting, or you sent someone a message, only within the last week or only within the last year, this constitutes an edge. You can think of how this edge kind of model is modeled, and depending on how you model, it's going to change the outcome of what you do, right? So you need to kind of think carefully about this. If you blindly just make your edges, then it will be less clear what the output of your whatever algorithm you run is. So it's important to think about how you model these edges, but for most effective purposes, we'll think of this as being like the friends on like the Facebook, or if you follow someone or that person follows you on Twitter, right? So this is the notion. This is maybe how you could be defining edges. All right. So this idea of studying these graphs and communities and kind of the structure of these graphs is actually a really old problem. But it's been completely revolutionized how people thought of this in the last, probably last decade, maybe last, like 15 years. Do you have a comment?
So, can graph contain only a similar kind of vertices? Like in social graph you're talking about, there are only people. Say, if I want to talk about IMDb graphs, it might contain vertices as movies, or even as directors or someone else.
Yeah, it's a good point. So there are lots of ways you can model these graphs. You can think of the vertices as movies, and then the edges as being whether they have either the same director or the same producer, or some other ways to constitute an edge. Right? So some other form or there's some notion of similarity between the movies, and if they meet some threshold, then you can say there is an edge. Or you can even do something softer, right? You could say there's an edge, a full edge is a value of 1, no edge is 0, and they could have some similarity which is in between. Right? So the more similar they are, the more 1. And a lot of these, well, some of the techniques we'll talk about will go through if you don't have binary edge values, if you have kind of some continuous edge value, you can still use some of the techniques we'll talk about. Yeah, so you could, like, for instance, if there are a couple things that we already talked about in earlier lectures. One was spectral clustering. And this is where you took the graph, you constructed the Laplacian of the graph, you found the first eigenvector of the Laplacian, and then you used this to kind of do a linear mapping of all the vertices, and then you found a cut there, and that kind of divided two clusters and recursively did that. You could do the same spectral clustering if you had continuously valued edges instead of 0, 1. You could still build the Laplacian in a similar way, and all this technique would go through. The other thing that we talked about was computing PageRank, and this was based on this theory of Markov chains and extending into these graphs. And so what you need to do here is to find the key part was this, turning the graph into this probability transition matrix. And so you'd need to think of how you would do that if you didn't have hard edges. But you could probably come up with it. You're more likely to go on an edge if it had a higher weight, a higher similarity. And so you could kind of adapt that and probably compute something very much like the PageRank vector, even with other versions of edges as well. Right. So there's lots of modeling choices in here, and I think you could extend both of these two techniques. Okay. So before I kind of get into it, so the plan today is to talk about like a variety of techniques for finding these communities in graphs, and even really what does it mean to be a community in a graph. So kind of at the first level of thought about this, you kind of just want to do clustering on the graph like we did before. And so by clustering, you can think of having these vertices, and you have edges in between them, and you want to say there's a lot of edges here and a lot of edges here, so this is one cluster, and this is one cluster, and so then this is one community, and this is one community. Okay, so this is the first straightforward way of finding these communities in graphs. But you know, it could very well be that there are some vertices that don't fit in any community, some vertices fit in multiple communities. So how do you do this? So it's a little bit more general. And so we'll talk about this. So we'll go through a few techniques, but before I do that, I want to kind of give an example of how the whole way this is, this sort of study of graphs has changed. So I'll talk about some mathematical modeling kind of second, but first there's kind of this problem that, so graphs are studied by sociologists a lot. Not a huge amount, but they would go and collect these graphs, and so they'd have it so that the number of vertices was roughly on the order of like 100. And so then the edges maybe were, and then maybe the edges were on the order of, say, like 300. And sometimes they're much smaller than this. Okay? And so there are a couple things that were different about graphs like this. So if they're this small, unless they were really dense and the number of edges was kind of close to n squared, you could often draw them pretty well. You could embed them in the plane, and you could use these spectral techniques and kind of get to the top two eigenvectors and use that to project this graph to the plane. You can kind of visualize what was going on here. With much larger graphs, that's a lot harder to do. They're also studying them at the scale. because this was about the scale they could actually collect them at. This was kind of before there were these automated ways where people were building these social networks all in computers, and so they had all this information stored. They would go to like the high school, and they would go and talk to a bunch of people in the high school and see which people had dated other people in the high school. And so these were like classic studies of graphs that people use. They would go and collect this, and this would take a long time to collect this information. So they had this data set that someone writes their whole PhD thesis on just this one data set of only this size. So if you imagine doing that now, you probably get laughed at, right? So this is a very small structure. So, so as an example of one of the questions they would ask is they would say that there's some graph and there's some known community in the graph. Okay, so let's say that there's some, people in here, and then there's also people who are not in this community, who are in this graph. And so let's see. So then there are two cases. That I want to highlight here. Yes. So everyone can see this. So there are two types of edges. So this community could have been like this was like a church group, and this was the entire kind of the 8th grade class in high school. So something like that, or maybe this was a club. This was like the chess club or something like that. And there are two types of people that they would consider. So there was this type A in blue here, and they had 3 friends that are in the group, and all these 3 friends know each other. Okay? The other case was this red person with 3 friends in the group, and these friends did not have edges between them. Okay? So the first example here, and what we want to say is which of these people is more likely to join this group? So you can imagine why this is an interesting question, right? If this group is a group that is, that you have built, let's say, a classifier on, you can advertise to this group fairly effectively, or this is a group of your paying customers. Which of these people should you try and target, for instance? Which of these people is more likely to do that? And if you know that this type of person is more likely to join, then you want to match up these people so they're friends, and then that will cause this person to be more likely to join. So you may want to spend energy building these connections inside. So it's a fairly interesting question, and this was like a debate in the community, and there were 2 theories that either this person will call this person X in blue and the person's red in Y here, okay, and so the person X who has 3 friends who are all connected in the group, and this person Y, so let's call this person Xavier, and this person Yolanda. Okay, so who thinks Xavier is more likely to join the group? Okay, and who thinks Yolanda is more likely to join? Okay, so start with Xavier. So why do you think Xavier would be more likely to join?
I just think intuitively you think, okay, that's kind of like a strongly connected component there. Maybe they'll all say, it just seems as though there'd be a stronger persuasion for them to join that one.
So you have 3 people in both cases, though. So, but you think there's kind of a stronger persuasion. So can you maybe try and formalize that a bit more? Maybe think about that.
He's indirectly connected to more people. If not directly, even indirectly, he's connected to, like, X is connected to 3 points, and those 3 points are again connected to more number of. So the sort of connectivity is high in case of X compared to Y.
So this part of the graph is denser.
Yes, yes.
Yeah, so I mean, they're both connected to 3 people, but this one is denser. And so, do you want to add to that, or?
I thought I did, but no.
Yeah, so kind of the argument here, and this was kind of kind of the computer science came to this, was that there was a bit more safety here, in that you would join this and you wouldn't just be going, you would kind of be going and joining a clique within the group, and this was kind of a more safer feeling. And this was kind of the whole, this was the scientific argument behind it before. It was hard to formalize, right? You know, why is this one better than this one? So on the other hand, there was also arguments for case Y, and at least you thought this was the case.
So that's maybe, for example, these 3 friends, because they're not connected, they're from different social groups. So one guy would see that, oh, for example, the students, doctors, and for example, workers, all of them are joining this group. So this means that this group is a good place to go. So let me go with this group.
Yeah, so good. So this argument was basically called independent support. Independent support. So if you would go, you'd have multiple types of groups to join. In fact, you might think, I'm going to join this group, and all these people may have other friends in this group. And so I'm more likely to kind of expand my network of friends by joining here, because there are all sorts of people I would meet. Right? So this was the choice Y, that they thought independent support, versus this one was kind of more, it was safer, because you were joining kind of a clique. All right, so this was the debate, and there wasn't an answer. People didn't have enough data sets, it was so hard to collect these, that they didn't really know which one was actually more likely. And so then, you know, the internet came along, and they saw these social networks develop, and they can track them over time, and they can go and kind of observe a bunch of these situations, and then see what happens. Does this person join this club? Does this person join the club? And see which one is more likely to happen. Okay, so now that we've seen the arguments, do people want to revote? Okay, so let's say, who thinks it's X, the safety in numbers, or the safety in the clique sort of thing? This is roughly 5 people. Oh, no, like let's say 8. And who thinks the independent support? Gaining votes here? Okay, 3 or 4. Okay, and 5. And which people didn't vote? Which people think it's equally likely? Okay. So they're all good guesses. People didn't know until they measured this. But it turns out that the X case, where they're forming more of a clique, is more likely to happen. There are lots of empirical measurements we've done, and now it's the science behind it says this is the right way to understand joining groups. It's more than just the number; it's also the density of the friends, if they're all connected. Okay, so so this is related to this idea of preferential attachment. So this is not exactly the same thing, but there's kind of a much more widely known phenomena that if you have a graph, and you're looking at which edge is going to be the next edge to form this graph. These, people join the graph, you get new nodes. People joining Facebook, they're going to add edges. Which edges are more likely to be added next? And you're more likely, let me draw here, you're more likely to form an edge that forms this new triangle. So this kind of corresponds to a similar phenomenon here, where forming this new triangle is more likely than adding an edge that's not forming a triangle. So if you have 2 friends, if you know someone who's friends with one of your friends, then you're more likely to have this edge here. You're more likely to form this edge. So this is known as preferential attachment, and it's pretty related to this phenomenon of how people are joining these groups. So another way this has kind of changed, and so this preferential attachment is kind of a fairly dominant model that we see in these large social graphs. The edges are not spread out evenly in these graphs. But up until we started being able to gather and observe them, you really couldn't really tell from these phenomena on this scale. So there were these models of random graphs. So, and the idea was that you would say the number of edges is n, and so that the number of edges, the number of vertices is n, and then you'd say that each edge in this graph, let's call this edge ij between vertices I and j. Actually, I'll use this notation later. So let's say edge ij. So this is going to be 1 with probability p and 0 with probability 1 minus p, where p is some probability, so between 0 and 1. Okay? And so this is known as the this is known as the Erdos-Renyi model of graphs. And there's kind of a very similar model where you said there are n vertices and then there are m edges, where m is some number between 0 and n choose 2, and these edges are assigned randomly without replacement. And so you can map that to a probability. But this was kind of a common model. People studied these graphs a lot. There's a lot of cool graph theory about this. And as you would keep increasing the probability p, you start to see different structural phenomena in the graph. At some point they become connected. At some point you start to see cycles of a certain size. You start to see cliques of different size. And there's been a lot of work under this model of random graphs. And people, you wanted to study graphs, but you said, what's going to happen when these grow? You say, well, maybe this is how they grow. Let's see. I'll say I have n vertices, and then I'll pick some p. Here, p maybe, you can figure out 300 over 100 choose 2, and that will give you p, and that's your guess of how the edges are distributed. So it turns out in large graphs, this is really not the case. It does not at all follow this property of preferential attachment. Okay? It follows the thing where if you're equally likely to choose these blue edge and the red edge as the next edge in your graph. So there's been a lot of work here, and so there are other models that kind of go along with this preferential attachment. So one way of doing it is just kind of, start throwing edges down and have a higher probability of adding an edge if it's forming a triangle. If it's forming many triangles, say if there were also some edges here, so now this is forming 2 triangles, then it's even more likely to be added. And you can construct graphs in this way. But this way it's pretty slow. If you want to, there are lots of statistical tests people try and do on these graphs where they say, construct a bunch of random graphs, measure the property, and so forth. And doing this at scale was pretty slow. So kind of one of the main accepted models of doing this is called a Kronecker product graph. And so this is, I'm not going to get into the details of this, but this is kind of, the Kronecker product is of 2 matrices where you kind of take one element, so if you have 2 matrices and you have, and these could be of different sizes, and you think of, for every element here, you kind of replace it with this whole matrix. So you kind of expand the dimensions of the matrix by multiplying the dimensions together. And so you kind of put a graph here, another one here, or the adjacency matrices, and you kind of multiply them together, and you get this bigger adjacency matrix of a much bigger graph. And those, if you do this with certain kind of initial graphs here, that can be kind of, there's some randomness you can throw in, then you tend to get graphs that look a lot like the sort of graphs we see in these large-scale social networks. So I won't get into details of this, but if you want to use a random graph process, this is a good one to look up. And there's available code online to do these and to gather statistics for you. Okay. So there are a variety of other kind of things that have come out of this preferential attachment. People have done studies where these triangles on the graph tend to be very important thing to try and measure. There's been a lot of work in trying to just compute where are all the triangles. If you have a really huge graph, you can't store it all in one place. You need to actually use MapReduce often or some other one of these scalable techniques to try and just figure out where are the triangles. And this is very useful in generating these and so forth. And so, for instance, one of the other things is people have seen that if you have a lot of edges, but not a lot of your friends are friends, so not a lot of triangles, you're more likely statistically to be like not as happy of a person. Where if you're in a clique where all of your friends are friends, then you're more likely to be in kind of a happier social situation. So that's also kind of another reason why people join these communities. They'd like to be part of cliques. This is some kind of sociology research that's come out of the availability and study of these large graphs. Okay, so the first kind of technique or new measurement we're gonna talk about is called betweenness. Okay, and what this is going to do is measure the importance of edges in graphs. Okay, and I'll talk about how once you have these betweenness properties, it's very easy to try and find these communities. Okay, so but this is saying so like the betweenness of AB. So this is an edge between nodes A and B. Is supposed to tell you the importance of edge AB. Okay, so like PageRank was telling you the importance of these vertices in the graph. Betweenness is telling you the importance of edges. But this is going to be a different model of how this works. Okay, and you can actually apply this betweenness to vertices as well, and it gives you a different value than if you're doing PageRank. This one is harder to compute though, as we'll see. So how this is defined is if you look at it's the fraction of all shortest paths in the graph that use AB. Okay, so if you have a graph, you go and construct all shortest paths between all pairs of vertices, and you count which ones use edge AB, and you calculate this fraction. So the higher the number of the shortest paths that go through edge AB, the higher the importance of this edge. Right? So if we draw an example graph here, okay? So this edge is going to have very high betweenness because any node, if I took from this side, any node from this side would need to have a shortest path go through this edge. So this is high betweenness, and this kind of tells you which edges are going in between different communities. So the high betweenness edges are the ones that are kind of the links between communities and are kind of the ones connecting different parts of the graph. Right? So if this is an important channel of communication in the graph. Okay, so you think of like if you think of in the internet, like these transatlantic cables will have really high betweenness. There aren't that many ways to get information from the U.S. to Europe. There are only sort of these fairly relatively small number of cables going under the ocean, these will have very high between-us scores. Okay. And so let me kind of demonstrate kind of, it's a little tedious to actually go through the calculation of this, but let me kind of show how this works. So think of one vertex here, and then I'm going to calculate the shortest path to every other vertex, and I'll draw that with an edge here. So the shortest path is this one here, the shortest path to this vertex is here, shortest path to this, so the shortest path is this vertex, takes two edges, shortest path to this one, marker sign, is here, and the shortest path to this vertex goes on this edge, across here, and up here. Okay? So now this edge is in the shortest path of 3 out of 5 of the cases, so 3/5. And so if I did, so this is only for one vertex, right? So I want to do this for all the vertices, so I need to then say calculate the, if I did the shortest path starting from here, I have an edge here, one going across, another one here, and another one going across there. So still, this vertex has 3/5 of the edges of its shortest path using this edge here. And so in fact, every vertex will have 3/5 of its shortest path using this edge. And so the betweenness here is going to be 3/5. So if you were to calculate this, it seems pretty slow, and you're right. So so you don't. So it's a little. So you don't want to kind of independently compute all of the shortest path. So what you want to do is for each vertex in the vertex set, you want to run Dijkstra's algorithm from V, and what this will do is it will, in time that it only takes to view each edge once, basically, will in O of E time will give you the shortest path to every other vertex, right?